Okay, today I'm going to talk about finding volumes of solids using the disk method. This kind of goes back to what we've been doing this year with flags, finding different volumes of shapes by taking a region and rotating it around a particular axis. The difference here is we're going to be generating shapes that we can't use typical geometric formulas such as the form of a cone or a sphere or something like that. So we have to use calculus to do that. So we're going to start here with a pretty basic one. So we're going to find the volume of the solid formed by rotating the region bounded by f of x, which is equal to 4 minus x squared, and the x-axis, and we're rotating it about the x-axis. So let me try to draw a picture of what that's going to look like. Please forgive me as far as my drawings go. I don't tend to do the best job with this, but I'll do my best. Okay, so let's start off with the region. So f of x equals 4 minus x squared. That's pretty easy. That is just a standard upside down parabola. You should have no problem graphing that. Okay, so the region we're talking about here is this region right here. Okay, so now what we're going to do is we're going to rotate this about the x-axis. And I'll tell you in this class, we're interested in a variety of different rotations, but they're always either going to be horizontal or vertical, and they're never going to cross through the region. So this one's pretty basic because we're rotating this thing about the x-axis. So I think in this particular case, we can kind of visualize what this shape is going to look like. So like I said, I'm not the best at this, but let me give it a try. So we're going to get kind of a, so if you imagine rotating this around, it's going to be, I guess, what would that be like? Almost like an egg. Something like this. Okay, so imagine that rotating around and that being 3 dimensions. Okay, so this is the shape we're talking about here. Now, this is not any shape we've dealt with in the past, so we don't have a geometric formula for that. Let me grab a calculator. Okay, so what we're going to do is we are going to do this similar to the way we do area. So let me just review how we talked about doing area. Same type of situation when we've done, in past classes when you did area, you always had a formula, it was a rectangle and you do width times length, or it was a circle, or whatever. You always had a geometric formula. And then in this class, we started dealing with finding the area under just sort of a random curve, call it f. And I think we all sort of think about this quite easily now. If I want to find the area under f of x from a to b, we know we're going to do the integral from a to b of f of x dx. But don't lose sight of what you're actually doing here. So what we're actually doing in these cases is we're slicing this up into rectangles. So at the beginning of the year, we started doing this by approximating, where we would find, maybe 10 rectangles, 20 rectangles. And the one thing that we came to the conclusion is the more rectangles, the more accurate it's going to be. So if we want the exact, we came to this conclusion that if we sort of slice this up into an infinite number of rectangles, okay, we can get the exact area. And that's essentially what this means, because when I slice this up into an infinite number of rectangles, what we have is the width of any one of these rectangles is approaching 0. And we denote that with the notation dx. So the notation of dx means an infinitesimally small change in x. So if you could think of like the smallest, or the number closest to 0 without actually being 0, that's what we're talking about here. So the width of any one of these rectangles would be dx, and then the height, depending on where we're looking at this from a to b, is going to be f of x. Okay? So the area of any one of these rectangles will be f of x times dx. I don't know why I'm saying rectangles that way. So anyways, f of x times dx will give us the area of one of these rectangles. And then what essentially the integral does from integrating from A to B is that essentially is going to sum up all those rectangles from A to B. And that's where that comes from. So we're going to do a similar type of thing with our volume here, but in 3 dimensions. So instead of slicing this up into an infinite number of rectangles, let's think about the shape that we're slicing this thing into. Okay, so if I slice this thing up, okay, so 2 dimensions, that ends up being a rectangle. But if I rotate that about the x-axis, okay, what I'm actually getting is what they call a disk. So if I think about slicing this thing up into an infinite number of these disks and then slide this out, right? Okay. And once again, this idea is that we're actually slicing this up an infinite number of times. So this disk has a thickness of dx. dx, once again, being this infinitesimally small change in x. So really what a disk is then, is it's going to end up being just a cylinder, a very, very, very flat cylinder, okay? And the height is actually this dx. So a cylinder is a very easy thing to find a volume for, right? So what we're interested in now is the radius here, because the area of the face would be pi r squared, and then dx, right? So that's going to give us the volume of any one of these really, really flat cylinders or disks. So that gives us one of those. And then with the same type of logic here, I'm going to want to sum up an infinite number of these. So that's where the calculus comes in. So when I do this disk method, okay, I am going to have pi, and typically pi being a constant, I'm going to bring out front of the integral. And then I'm going to integrate from A to B. So in this case, well, let's just keep it. Okay, so this is our formula for a disk. Pi out front, integral from A to B of r squared dx. So now what we have to do is just think in this case, what is our, what's our A to B and what is our r squared dx. So in this particular case, so we have our pi out front, A, we're starting here at -2, and we're going over here to 2. So that's going to be -2 to 2. And then our r, if we think about this, our r is just going to be f of x. Just like our length of our rectangle in a 2-dimensional shape will be our f of x, in this case, our r is going to be f of x. So I'm going to take f of x squared and then dx. Now, what I'll tell you is, if you see this on the AP test, if it's closed calculator, which sometimes it is, in this type of problem, this would actually be quite involved to actually evaluate this by hand. So quite frequently, they'll have you just do the setup and leave it there. So this is the setup, f of x being 4 minus x squared, that's going to give us the volume of this shape. Okay. Since we have my calculator here, what I'm going to do is I'm just going to use Math 9. So now we can actually find the volume by using Math 9, if this is like in an open calculator setting. So let's go ahead and figure out what that is. So let's see, Math 9, -2 to 2. Let's put our function in there for minus x squared. And I want to square that thing. And then x, and I get 34.13 repeating. So that's 34.13 repeating pi. So you could leave that in terms of pi. Make sure your answer is always accurate to 3 decimal places. Or I can just multiply by pi, and I get 107.2330. So these are the 2 choices that I would go with here, and that is the volume of this shape, and that is the disk method. At some point we'll be doing AP type problems where, you know, they give you like a function and different attributes, and then you're going to answer various questions. In that case, I'd probably put this in my calculator as y sub 1 or something like that, so I would have access to it multiple times. In this particular problem, that's not really necessary once I calculate it. So that is disk method. And that's something that we're going to be using for finding any volume that is formed by a solid cross-section.